Hello class, today we're going to move on to Unit 8, Lesson number 5, which is 8.5, Solving Exponential Equations. So some of this is going to be a little new to us, and then some of the word problems, the setup of them will be familiar from last year. So let's start off with the method for solving an exponential equation, which is finding a common base. So this should be a little familiar to you. We actually did a little, touched on a little bit of this in previous lessons. So that states that if you have a base to the x equals that same base to the n, so you have these two powers equal to each other, both with the same base but different exponents, the only way that they can be equal to each other is if the two exponents are equal. So in this case here, x equals n. So our goal then is to always try to make the left side and the right side powers with the same base, okay? And that's called the common base method. So we're going to solve this by finding a common base. So we have 5 to the 2x plus 3 equals 1 over 125. So we've got a base of 5 here, so that means we want to rewrite this side as a power with a base of 5. So immediately we know that we can write 125 as 5 cubed. So that means this is going to be 1 over 5 cubed. Again, we need the powers to be on the same level. In order to bring this power up to the top, that means the exponent will have to change signs. So it's going to become negative 3. So we get 5 to the 2x plus 3 equals 5 to the negative 3. And then this rule up here states that that means if they're equal to each other with the same base, that means their exponents must be equal. So 2x plus 3 equals negative 3. And then from there, you're just solving a linear equation. So you're isolating for x. So we're going to bring this 3 over. So 2x equals negative 3 minus 3. So 2x equals negative 6. And divide 2 from both sides. And we get x equals negative 3. And we just solved an exponential equation. Next we have 8 to the x minus 1 equals the third root of 16. So here, the first thing you might want to do is get rid of the radical symbol. So write this radical as a power. So we're going to write that as 16 to the 1 over 3. Now our problem here is that we've got a base of 8 here, base of 16 here. I cannot write 16 as a power with base 8 easily. That won't be easy. So we have to think how can we write 8 and 16 as powers with the same base? So this is where kind of becoming familiar with your powers is going to help out. If we can write 8 as 2 to the 3, and we can write 16 as 2 to the 4. So then they have a common base. So it may not always be the ones that just appear there. So we're going to write 8 as 2 to the 3, and that is all to the x minus 1 still, okay, right here. 16 is 2 to the 4, and remember that whole entire thing is raised to 1/3. So what's going to happen here is when you have a power to a power, remember you have to multiply. So that's why I'm showing the distribution. So here we're going to get 2 to the 3x minus 3, and then 2 to the 4 over 3. So now that the bases are equal, we can equate their exponents. Right, so we can make this equal to this. So 3x minus 3 equals 4 over 3. We're going to bring that negative 3 over, so it becomes plus 3. So then you need to have a common denominator here because you've got a denominator that's not equal to 1 here. So we're going to do an LCD of 3. So that gives us 3x equals 13 over 3, and divide out 3 from both sides. And that will give us 13 over 9. Okay, so 13 over 3 divided by 3 is 13 over 3 times 1 over 3, which is 13 over 9. All right, 49 to the x minus 1 equals 7 times root 7. So again, I would immediately rewrite root 7 as 7 to the 1/2. So what we can kind of see here is that we can write 49 as 7 squared. Okay. and then all to the x minus 1. And then here, notice, remember the rule here, when you multiply powers with the same base, you add their exponents. So that's why we're doing the 1 plus 1/2. So that's going to leave us with, so remember here, you're going to have to distribute, because power to a power means you multiply. So you get 7 to the 2x minus 2 equals 7 to the 3 over 2. Right? That's what 1 plus 1 over 2 is. All right, so now we have the same base, so we can equate their exponents. Okay. So 2x minus 2 equals 3 over 2. We're going to bring the 2 over, so it's plus 2. Again, here we've got this rational number here, so we're going to find out LCD of 2. Multiply top and bottom by 2. And that is going to bring us to 2x equals 7 over 2. You're going to divide out 2 from both sides. Okay. Divide out 2. Divide out 2. Okay. And you're going to get x equals 7 over 4. Okay, so now we're going to try our second method for solving, and this involves common factoring. So really focus on this one. This is the one that really confuses students a lot, but just make sure you practice and you'll see the patterns easily. So for this one, it's going to involve us having to go from something where we have a to the x plus y, so a base and then the addition of two parts in the exponent. And we're going to actually have to write this, so we're going to actually have to kind of factor it a little bit. We're going to have to write it as a to the x times a to the y. Right? That's the operation if we were to work backwards. So just like up here we did 1 plus 1/2, now it's as if I give you this and we're going to go backwards to this. And you're going to see why. So it says solve for x here. So the first thing you want to do, when you see you have a 2x plus 2 and then plus, so notice there's a plus sign here, so I can't do anything with the next term for the 2 to the x. Okay, so there's no operation that says I can combine these two and there's a plus sign in between, even though they look similar with the same base. So what you're going to do to help you is you're going to write 2 to the x plus 2. You're going to work it backwards. So you're going to write it as the multiplication of its two powers. So we're going to write that as 2 to the x times 2 to the 2. Okay. So right there in purple, so here let me highlight this. Okay, so right here, 2 to the x plus 2, we rewrote as this, just using our exponent laws. And then we have the plus 2 to the x equals 320. All right, so again, we can't do any combinations here with a plus sign. So now I want you to take out a GCF of 2 to the x. So here in this little green section here, so on the left side only, I want you to take out a 2 to the x from this term and from this term. So when we take out a 2 to the x, we're left with this part left, so 2 squared, and then plus 1, because 2 to the x divided by 2 to the x is just 1, and then equals 320. So let's simplify the brackets now. So that is 2 to the x times 5 equals 320. Again, the whole point is to isolate for x. So I want to isolate the 2 to the x term first, so we're going to divide out 5 from both sides. Okay, so we're going to do 2 to the x equals 320 divided by 5. So 2 to the x equals 64. Now we can do the common base method, which is what we just practiced above. So we can write 64 as 2 to the 6. And because the bases are the same and they're set equal to each other, that means their exponents are equal. So we just found out that x equals 6. So that's kind of a really pretty cool way to solve something like this. Again, I want you to recognize the way that the equations look when you have to use this method. Okay, so it's usually the addition or subtraction of two terms with the same base, where you were factoring out the base to the x is usually helpful, right? So here you had 2 to the x plus 2, there we have 4 to the x plus 3, and then we're subtracting 4x. So let's do the same pattern. Let's rewrite 4 to the x plus 3 as the product of two powers. So 4 to the x times 4 to the 3, and then the rest of the equation remains. Now we're going to take out a GCF of 4 to the x. Okay. So here we're going to do a GCF of 4 to the x. Okay. So we took that out here, and then we're left with 4 to the 3 minus 1. Okay. Something divided by itself is just 1, and then there was the negative. So 4 to the 3 minus 1 can be simplified to 63. So 4 to the x times 63 equals 63. Because they're being multiplied here, and we want to isolate 4 to the x, we're going to divide 63 from both sides. So we're going to get 4 to the x equals 63 divided by 63, and that's 4 to the x equals 1. Okay. And if we wrote that as a common base, we know that the only way you can get 1 from an exponential or from a power is if you have a base raised to 0. So when we do a common base, 4 to the x equals 4 to the 0, so that means x equals 0. All right, let's try another method. So the next method for solving something that perhaps cannot be helped with common factoring and cannot be helped with common base. Obviously, common base isn't always going to work. The next trick is to take the log of both sides. So when exponential functions cannot be solved with a common base, take the log of both sides of the equation. And when you do this, you're doing the common log. So you're doing log of base 10. Okay, when you do that, when you take log of both sides, that means you're able to use a calculator. All right, so it says solve for x given 6 to the x equals 231. So we definitely can't do a common base for 231 as 6 to the something. So what we're going to do is take the log of both sides. So I'm going to take log of 6 to the x, and then I'm going to say that's equal to log of 231. Okay, so same rules as our other operations. Whatever you do to one side, you have to do the other. Okay. All right, now we're going to use our log laws from previous lessons to help us simplify. So I want you to think of the power log law. Okay, so that says log of a to the x is equal to x times log a. So it means that you can always bring that exponent down in front and multiply. Okay. So let's do that here. So I'm going to bring the x down. So we get x log 6 equals log 231. And then you want x on its own, so you're going to divide out log 6. Okay. Remember, log and a number are a package deal. So you can't just divide out the word log, just like you can't divide out the word sine. Like sine has to have an angle with it, or else it doesn't make sense. So log is the same thing. It has to be log of something. Okay, so sometimes students will divide out the word log. That doesn't really kind of imply anything. So you have to do log of a number. So log 6 are a package deal. You're going to divide that out of both sides. Okay. So x is going to be equal to log of 231 divided by log 6. You can use your calculator here, and everyone should be trying this to make sure they get the right answer. And let's round to 2 decimal places unless told otherwise. And that means x is equal to approximately 3.04. All right, let's go to the next page. All right, let's try this one. Again, we have 2 to the x plus 1 equals 3 to the x minus 1, and we have to solve to 3 decimal places. So in this case here, right away when I saw the 2 and 3, I know I cannot easily write them both as a power with the same base. So that's a hint that right away I can't do common base, I can't do factoring, that's not going to help us in any way here. It's a hint that we're going to have to take the log of both sides. Also another hint is the fact that I say here round to 3 decimal places, so that usually means the log button had to be used. Alright, so let's take log of both sides. So log of 2 to the x plus 1 equals log of 3 to the x minus 1. So remember, we're going to do the log law where we bring the exponents down in front and multiply. Okay. So that's going to be x plus 1 times log 2 equals x minus 1 log 3. So Next, because this is multiplication, so the tricky part here is that you want to try to get x on its own. The only way that you can get x on its own when it appears in two different product pieces is that we're going to have to expand this out and then collect our like terms with x. Okay, so we're going to do x times log 2 plus 1 times log 2 equals x times log 3 minus 1 times log 3. Okay. So we get x log 2 plus log 2 equals x log 3 minus log 3. So again, I want you to kind of notice your like terms. So x log 2 and x log 3 are like terms because they both have the term, the variable x, and their coefficients are essentially log 2 and log 3. We have two constants, which is the plus log 2 and the minus log 3, so we want to group those together. Okay. All right, so I brought all my x terms to the left, so x log 2 minus x log 3, and then all my constants to the right, so equals negative log 3, and then it comes over here, becomes negative, so minus log 2. Keep in mind, I do not want you rounding until the final step. So I don't want you entering into your calculator what log 3 is, and then writing that decimal out, okay? That's not proper form. You leave it like this until the final answer. Okay, so if I collect like terms here on the left side, we've collected the like terms here, but now I want to find a way to combine this. So let's take out a GCF of x. Okay, so if I take out a GCF of x, that means I'm going to be left with x times log 2 minus log 3. Okay, so that's in the brackets. And then the right side remains. Okay, so again, our goal when solving is always to get x appearing once on its own. So now, because x is multiplied by this number, log 2 minus log 3, that's basically the coefficient. Okay, looks like an ugly coefficient, but it is one. So you're going to divide that out from both sides to isolate x. So divide out log 2 minus log 3 from both sides. So in your calculator, you're writing negative log 3 minus log 2 divided by log 2 minus log 3. So make sure you keep brackets. Depending on the calculator, the brackets will be very important. And you should get a final answer of, again, everyone practicing on their calculator, a rounded value of 4.419. Good. So basically, when you can't do common factoring to help yourself, and when you can't do common base, take log of both sides, and then keep going with log laws. Okay, so now let's move on to exponential, some word problems, and these should be very familiar to you from last year. Okay, so not really any new concept here, we just have new ways of solving for x. So the compound interest formula is used a lot for exponential, and just to recall, that's a equals p times 1 plus I to the n. So remember, a means the final amount, p represents the principal, so the initial amount, little I is the interest rate per compounding period. So for example, if it's compounded monthly, interest rates are given per year. So if I want the interest rate per month, that means I'm going to have to take the interest rate per year and divide by 12, okay, if it's monthly. So the general way to calculate I is going to be the annual interest rate, okay, divided by the compounding frequency per year. Okay, so that's the per symbol, okay, so per year. Right, so if it's compounding frequency of quarterly, then that's 4 times a year. Okay. Or actually, you can just read that as compounding frequency in 1 year. That's probably what I was trying to write before. Okay, so per year or in 1 year, same thing. All right, so that part you're always going to have to calculate because usually the question only gives you the annual interest rate for a year. Okay, so and then next one is little n equals the total number of compounding periods over the time of the question. So it'll give you something. And this always has to be in years. So for this one, or the total number of compounding periods, they're always going to give you time in years. So to calculate n, you're always going to have to do number of years times the compounding frequency in 1 year. So in this case, if it's in an investment for 5 years, and it's compounded quarterly, so 4 times a year, you're going to have to do 5 times 4. So that means the total number of compounding periods is 20 compounding periods a year. And another note here, remember your I value has to be in decimal form, not in its percent form. Okay, so let's practice here. It says if 2,500 is invested at 4.8% slash A, so slash A means per annum, which is another way of saying per year, compounded quarterly, so quarterly means that the compounding frequency is 4 times a year. It says how long in years will it take for the investment to reach an amount of 4,000? All right, so the biggest problem here is that sometimes students, when I say how long in years, you have to remember this formula up here. So number of years is technically not the letter n. Okay, so the letter n is the number of compounding periods. So we're asking for the number of years. So I sometimes tell myself, I say, I pick another variable. So I say let x represent the number of years. So then that means when I'm looking for my n value in the equation, that means my n value is actually 4, okay, 4 for quarterly, okay, compounding frequency, 4 times x, right? So I'm using this formula here, okay? My x is the number of years, compounding frequency is 4. So n is equivalent to 4x, and then that will help me to remember that whatever answer I get at the end, I'm going to have to isolate for x by dividing it by 4. Okay. So what else did they tell us? They told us that we want the investment to reach 4,000. So A is 4,000, the future value. P is 2,500, the amount invested. And little I, we're going to have to do 4.8% in decimal form is 0.048. Right? So you always take that value in percent form and divide by 100. And then you have to take that and divide it by, so you have to take that rate and divide it by the compounding frequency in 1 year, which is 4. So we get an I value of 0.012. Okay, so that's the interest rate per compounding period. All right, so let's plug everything in that we know. So we get 4,000 equals 2,500 times 1 plus 0.012 all to the 4x. So again, we want to isolate the 4x. Right now the 4x is a package deal with this base right here. So the first thing we want to do is divide out 2,500 from both sides. So we're going to divide out 2,500, and that will give us 1.6. Okay, 4,000 divided by 2,500 is 1.6 equals 1.012 to the 4x. We're definitely not going to want to do common base here, so let's take the log of both sides. Log 1.6 equals log 1.012 to the 4x. The next thing we can do is our log law, which says that we can bring the 4x down. Oops. Down to the front. Okay, that'll help us. That'll help us with isolating. So we get 4x down to the front times log 1.012. So right away you can notice that the two coefficients here are 4 and log 1.102, right? They're both being multiplied by x. So do it at the same time. So let's divide 4 and log 1.02 from both sides, right? Because essentially we want x on its own. So in your calculator you're typing log of 1.6 divided by 4 times log 1.012. Okay, so you're just doing it all at once. And your final answer should be that x is approximately 9.85. Okay, and remember x was number of years. So therefore it will take approximately 9.85 years for the value to reach 4,000. All right, now when something isn't just an investment or compound interest related, it might just be something revolving general exponential growth and decay. So in that sense, the general exponential formula is f of x equals a times b to the x, where f of x is the final amount after x amount of time. Okay, a is the initial amount. B is the growth or decay factor. Okay, so I want you to keep in mind here, that's the factor. So that's very different than if the question talks about the growth or decay rate. So the growth or decay rate is denoted by lowercase r. Okay, so how does lowercase r relate to b? So if it's a growth factor, how do you find the growth factor? How do you find b? Well, b is going to be equal to 1 plus r, okay, if r is growth, okay, growth rate. Because that means you keep 100% of yourself and then you add a percentage of yourself each time. Okay. Decay is the opposite. That means you don't keep 100% of yourself, you're going to lose a certain percentage. So you do 1 minus r when r is the decay rate. Okay. And x in this case is time, and it could be days, months, seconds, whatever the question gives you. So it says Jamie bought a car for $25,000. It will depreciate 23% every year. So depreciate's another way of saying decay by percentage, so that's exponential. So if it depreciates by 23% every year, that means the decay rate, little r, is 0.23 in decimal form. He plans on selling the car once its value is $5,000. How long will Jamie own the car? Okay, so in this case here, we know that we're going to have to deal with f of x equals a times b to the x. Okay, so let's let x, make sure you give a therefore or let statement. So let's let x represent time in years. The reason I'm choosing years, okay, so I'm going to highlight this here. This is blue. Okay, so time in years is chosen because the decay rate was in years. Okay, so right here. Oh, that's not going to help us to see it. Okay, so every year. So because the rate was per year, I'm going to do time in years so it matches up. Okay. So we're going to let f of x represent the value of the car. All right, so let's fill in what we know. So we know what what the value of the car has to be for us to solve for x. So we know f of x is a $5,000 value. Okay. The a is the initial amount, so that's 25,000. And the b value we're going to have to calculate. So that is going to be, because it's decay, it's going to be 1 minus r. So 1 minus 0.23. Okay, which gives us 0.77 as our decay factor. Okay, so 0.77, if you're wondering what that number means, it means that the value of the car maintains 77% of its value every year. Okay, so the rate tells you how much it loses. The factor tells you how much of itself remains. And then obviously x is our question mark because it's asking how long, so time. All right, so let's fill it in. So we get 5,000 equals 25,000 times 0.77 to the x. Again, we want to get this isolated because it has x in it, so we want this power isolated. So let's divide out 25,000 from both sides. So this results in 0.2 equals 0.77 to the x. Again, not common base friendly, so log of both sides. Okay. And then you're going to bring that x down in front. So you get log of 0.2 equals x log of 0.77. So the coefficient with x here is log 0.77. You're going to divide that out of both sides. And that will give you a final answer of about 6.16. So therefore, he will own the car for 6.16 years, okay, before selling it. All right, and our last example here. Now keep in mind half-life, you've probably seen that a bit in science. That is just a formula in which it says it right in its name, right? A half-life, so it maintains half of itself every time, or you can think that it loses half of itself every time. So in that case, the b value is 1/2. Okay. Now this formula here is similar to the previous one of a times b to the x, just with a little tweak to it. So I use f of t. I'm just doing t just so that you can differentiate the two equations. Essentially, t and x are the same thing. So f of t equals a times, and then our b value is 1/2. And then here's the little addition. So you do time divided by h. So t divided by h. So what's different? So t is the time that's passed, okay, just like x was in the previous equation. And then h is the half-life time. So that's the time it takes to lose 50% of itself. Okay. So that's going to be the little added part here, that you have to do time divided by h. Keep in mind that t and h must be the same unit. Okay, so if the half-life was in days, then time has to be in days. If time was in seconds, then half-life has to be in seconds. All right, and we've got Jamie again here, busy person. He works in a laboratory that uses radioactive substances. The lab received a shipment of 200 grams of radioactive radon, and 16 days later, 12.5 grams of it remained. What is the half-life of radon? So right away, that question made it clear to us that we have to find h, the half-life time. So let's let t represent time in days. The reason I'm choosing days, again, you want to pick something that matches with the other units given. So the only other piece of information given was this here, 16 days later. So the time span of this was in days, so let's maintain that here. And let's let f of t represent the amount of radon remaining in grams. So f of t, right, was 12.5, right? That was what was there at the end. A is the initial amount of radon, which was 200. Okay. T is the time that has passed. So the information they gave us here was 16. Okay. And then h is our question mark. Okay, and remember that these two units are in days. All right, so there's our general equation for half-life, and now let's plug it in. So 12.5 equals 200 times 1/2 to the 16 over h. All right, same idea. Let's divide out the coefficient of the power here, so 200 from both sides. Okay. So then we're left with 0.0625 equals 1/2 to the 16 over h. We're going to take log of both sides, as always. Okay, we're going to bring down the exponent of 16 over h. Okay. Down in front. So we're going to get log 0.0625 equals 16 over h times log 1/2. And then, of course, we want to get rid of the log 1/2 from both sides. Okay. So you're going to divide these two on your calculator. Okay. And you should get that it equals 4. So 4 equals, okay, and then we're left with 16 over h. So remember, you want to isolate for h, so you're going to have to cross multiply. Okay. So you're going to get 4h equals 16, okay, and then we're going to divide out 4 from both sides. So we get that h equals 4. So remember the unit of measure, so that's days. So that means the half-life of radon is 4 days. And that is how we can solve exponential equations using some of our new methods. All right, I hope everyone enjoyed this. Make sure you do all the homework questions here, or as at least a minimum of half, and do more if you need practice, and let me know if you have any questions. Good luck.